As we get into our chairs, I'm gonna relieve Paul for a little bit as MC. So a few reminders. If folks have been participating in the group poem, there's a little basket on the table out there. You can add your whatever the muse tells you. But there's gonna be a group poem we're putting together, and then Julia in the back. Hi, Julia. Julia's got a few things going on back there. So membership to Prince William Sound Stewardship Foundation and the shop, and also the auction, right, Julia? All those things. So Julia's back there if you'd like to participate in any of those things. And I'm a member of the Stewardship Foundation and pretty psyched about the work. So it is membership supported. So I want to put a plug in for that. And tabling going on still for RCAC and Chugach Regional Resources Commission, the Coral Project, and the Forest Service has a few things there, including heritage. So that brings us up to our updates, and it's a pleasure to introduce the next speaker, Dennis Staley. And we were just talking about this. Dennis and Dave Snyder as well, I think, have participated in this event for 4 or 5 years. And then as a Forest Service guy working with Dennis, it's always been just really great. Dennis and Dave both just very easy to work with, very conscientious people, and doing pretty fascinating work. So the science behind monitoring operations at the Barry Arm landslide is our next discussion by Dennis.
Thank you for that very nice introduction, Tim. It's a real honor to be back here again this year. Like Tim said, this is my 4th time presenting to the group. For those of you who don't know me, I am Dennis Staley. I'm a research scientist at the USGS Alaska Volcano Observatory, where I moved up here in 2021 to focus scientific efforts towards the Barry Arm landslide, and eventually have expanded our geographic scope to other places in Alaska. So my role at USGS is to be the USGS lead for a multi-agency project focused on landslide and landslide-generated tsunami hazards throughout the state of Alaska. Today I'm going to be talking a little bit about how we're monitoring the Barry Arm landslide, and then more importantly, a little bit about why we're monitoring it in the way that we are. So for those of you who aren't familiar with the Barry Arm landslide, I made the mistake of putting animations in. So it's a large 500 million cubic meter landslide lurking in the northwest corner of Prince William Sound. And if it were to fail rapidly and catastrophically into the water, it could generate a wave that would be regionally impactful. This landslide itself is 1.5 miles wide by about 3,600 feet high, so a giant out there. And if you look just slightly up valley, up the Barry Glacier, there's another one that's also rather sizable, at about 150 million cubic meters of material as an estimate. So this landslide was recognized as a hazard back in 2019 by a citizen scientist. Many of you might know her. But she reached out to her brother and said, hey, I think I see a giant landslide out in Barry Arm. And so Higg then brought together a group of citizen scientists, academics, government scientists to write an open letter where they said there's this giant landslide out there and we think it has a big regional, it presents a big hazard for the region. So obviously the media took note of this, the federal government took note of this, and so lots of articles came out right around mid-2020 and into early 2021 with estimates of devastating waves approaching our harbor here in Whittier. So the USGS came in early 2021, and the first thing we did is we applied some refined landslide modeling and incorporated new bathymetry that the original group of scientists didn't have at the time to come up with an estimate of what that wave generating potential of the landslide is. And so out in Barry Arm, it's Lituya Bay plus. So for those of you who don't know Lituya Bay, it's the largest recorded wave run-up in history. So 1,700 feet high, the wave ran up on the opposite side of the shore from Lituya Bay. We have a similar scale of impact out in Barry Arm for this. But one of the biggest concerns is what is going to happen out in the fjord here. And so my colleague Katie Barnhart used new topobathymetric data and some refined landslide modeling to estimate the time of arrival and the maximum wave height out about 200 meters offshore. And so in her worst case scenario, which is represented by the darkest purple line on your screen, you'll see that she estimated about a 2-meter wave arriving in Whittier maybe 20 to 25 minutes after failure of the Barrier Arm landslide. So there are differences in model results that are out there. There's likely to be more as more people attempt to realize what the worst case scenario for Barrier Arm is, and that's great, that's science. But all of the models agree that the wave is going to arrive, an impactful wave is going to arrive somewhere between 20 and 25 minutes of landslide failure. That's an important point to consider when you're talking about monitoring and warning. And so that 20-minute failure, if you're based solely on detection, you don't have much lead time to let people know that something happened and you have a potential for a wave arriving in the harbor here. So we have crafted our monitoring strategy around two things. First, the landslide is an incredibly hazardous place to be. There's these huge gaping cracks, there's rockfall, there's snow avalanches, there's shallow landslides all the time. So we have chosen as a team to prioritize crew safety. And so the normal methods for measuring deformation, where you put holes in the ground and put instruments in those, we've taken off the table. All of our instrumentation is focused on remote sensing. If it's terrestrial, if it's from across the fjord, or things that are installed adjacent to the landslide that may give us some insight into what's happening on the landslide itself. So that's our first consideration. The second is that we want to monitor what we think may be potential precursors to catastrophic failure. This would give us a sense that something may be happening within the landslide, the stability of that mass itself may be decreasing, and we may have situational awareness that there could be the potential for rapid and catastrophic failure. So if we look back in throughout history of the landslides that have had people paying attention to them either prior to their failure or leading up or afterwards, there was a review of these 33 catastrophic landslide failures. 90-something% of those all exhibited some precursory evidence prior to catastrophic failure. And so precursors could operate over the days, weeks, months, years, even centuries leading up to an event. So that makes it a little bit tricky to untangle what's a precursor right before a failure versus what's leading up to a failure. But there are common ones, and those include deformation of the landslide mass. You'll see elevated rockfall and shallow landslide activity on the landslide itself. You'll hear unusual noises, and there will be seismic activity that can be recorded at nearby seismometers. So we have then put out a set of instruments that allow us to measure these precursory conditions. And so I'm going to start out by focusing on deformation and rockfall and landslides. And we do that primarily at our ground-based radar site. But before I get into that, I want to talk a little bit about the conceptual model we have for landslide failure. And so this is a classic model that's applied to these large, slow-moving, deep-seated landslides that progress over time and eventually can potentially fail catastrophically. And so what we have is a three-phase progressive failure model, where over time the mass itself accumulates strain from gravity, from tectonic activity, from other natural phenomenon, where you develop these sort of these cracks in the subsurface that aren't critical. They don't cause the entire landslide mass to necessarily move, but they propagate their way through the mass and start to develop this plane over which slip could potentially occur in the future. And so over time, that strain continues to increase. And then finally, you see a propagation of a shear surface or a failure plane or multiple failure planes throughout the mass. And so that's where you get critical crack expansion, and you have the potential for rapid landslide acceleration. And so that's where we see probably Barry Arm is in this tertiary phase of the progressive failure model. And so it's translated at least 100 meters downslope in places. So we have a clear development of a shear zone, of a failure plane. And what we're worried about now is acceleration of the landslide mass that could be indicative of that final stage of this progressive failure model. That differs rather significantly from the types of shallow landslides that occur in southeast Alaska during heavy rain. So we're applying a different approach to it. Our monitoring for Barry Arm is much different than it would be in southeast Alaska for these shallow landslides that develop over the temporal scale of minutes to days. So we've learned a lot about these potential precursors through the analysis of historic landslides. And one of the most famous ones was back in 2010 in Canada at Mount Meager. And basically, this entire flank of Mount Meager collapsed in a two-phase progressive flow, where it started off as a big landslide that mobilized as a debris flow, caused all kinds of damage downstream. Luckily, no fatalities because it was a very remote place. And then there was a second phase of a rock avalanche near the tail end of the event itself. This is an important one because we were paying attention to this slope for many years prior to Mount Meager failing. And so if we look back through historical imagery, we can see that there's a representativeness of the progressive failure model on the surface here. You get the development of surface cracks. There's clear scarps that show up in the imagery. You have these failures that are occurring through time leading up to the bigger failure. So this is an important event because we saw in a nearby location for Barry Arm that these things, how they evolve in this type of landscape. This is a volcanic rock down in British Columbia, so different than what we have here. But it also was one of the very first landslides where we had instrumentation that was sensitive enough to detect the effects of this in the seismology. So distal seismometers were recording this event too. And so it's one of the better studied landslides in many ways that have occurred recently. So getting back to Barry Arm, we're looking at deformation. And we can look at deformation over different time scales. The greatest gap in time from one measurement to another is through our remote sensing efforts. And so our friends at the state of Alaska, they fly LiDAR over the landslide every year on average and are able to get elevation differences. So the red shows where the ground surface has lowered and the blue shows where the ground surface has increased, at least as you perceive it through that measurement. So more likely it's a lowering of the top part and sort of a bulging outward of the bottom part. And that happens on the scale of about once every year we can make those measurements. So great for understanding landslide kinematics, but not necessarily for understanding how hazard evolves throughout the year. The graphs on the right show satellite INSAR. This differential INSAR is measurements are made every couple of weeks. Really only work well in the summer. The snowpack interferes with the signal. But when you start seeing those rainbow fringes, that means that the landslide is actively deforming. But again, it's a 2-week window that we're making these measurements. So it's not great for situational awareness that something is actively happening. It's just confirming that movement has happened in that past period. And that's where we bring in our ground-based radar instrument. And so within this hut that you see with the big white window, this is located on the opposite side of the fjord. So behind the person taking this picture is the landslide across the water. So within this enclosure, there's a radar system that sits on a 2-meter long rail, and it slides back and forth. And depending on the time of year, it can scan the landslide every 6 to 15 minutes and get some sense of how much that landslide has moved between each scan. And so once you start stacking those scans up together, you can get a very good high spatial and temporal resolution picture of how that landslide has moved over a period of a few hours, of a few days, over a few weeks. So I'm going to refer to a few features. So this camera is situated right at the radar site. It's at high resolution at the time, but technology evolves so fast. Takes a picture maybe once every hour or so, and there's a feature that we call the kite, the prow, and the core. And so I'll refer to these a little bit here in the next few slides. So when we turn on our computers in the morning and log in and take a look at the radar, this is what we like to see. We like to see lots of green. Green is indicative of zero movement or movement away from the radar system, but that doesn't really make sense for landslides. So we like seeing this sort of lighter green picture that you're seeing here, where there's really no movement across the landslide mass. There's some little pockets of different colors that you'll see. Those are just active piles of rock that have ice in them and like to move down slopes. So they do that all year long. But the color scale is what's important here. So green is zero deformation. Once you get in the reds, you're about 50 millimeters per day of deformation. Purple's 100, light blue is 150, and dark blue is 200. So what we don't want to see is things going from green rapidly to red, purple, or blue. That means the landslide is accelerating. So this was August 21st of 2022. This is August 23rd of 2022, where the feature of the kite started creeping downslope, pretty much overnight. And for context, the kite itself, the mass, the volume of that feature is in the neighborhood of the landslide that failed in Lituya Bay. So about 50 million cubic meters. So should that fail, again, there could be a regionally impactful tsunami, and particularly one that's for those that are situated in Barry Arm itself. So 23rd of August, we see some acceleration of the kite. This continued throughout the month of September, and now we're starting to see those scary purples and blues spreading out across the landslide. So the movement that was constrained, at least initially locally to the kite, then expanded out to the entirety of the landslide, and we saw a progressive acceleration of those rates of deformation throughout that month and a half, or excuse me, about that month period. Fortunately, about a month later, it decelerated, and so we shift from those purples and blues back to the yellows, oranges, and reds. So a decelerating landslide doesn't necessarily mean it's less hazardous, but it is a chance to kind of step back and take a deep breath and say, okay, at least we're not accelerating right now. But the hazard potential is still there without a doubt. And then finally, back in early November, it got a lot colder. The precipitation that was coming down fell in the form of snow, and the landslide pretty much shut down at that point. So we returned to a phase of zero deformation, and then we got in the winter and we sort of lose track of it as the snow piles up on the landslide itself. So that's what an episode of deformation looks like from our radar system. And you can see how it's tricky. If you're looking for acceleration, acceleration doesn't always mean that the landslide is going to fail. We've seen that a number of times through the history of the Barry Arm landslide as people keep track of it in different ways. The fact that it isn't moving is also not necessarily means we're out of the woods. You can have a large regional earthquake that shakes things loose. So have all of those things in mind. But the biggest thing that we get concerned with is that acceleration of the landslide, especially as it expands across the full body of the feature itself. Deformation is one thing we want to keep track of, and we do that in a couple different ways. We also are concerned with what could be potential precursors in the form of rockfall and shallow landslides. And so here we're using imagery, just ground-based cameras, to keep track of what's happening. So here's a picture from the 24th of October, 2022. We've got, I'm just going to highlight this area because it's a little bit hard to see. Next day, we get some snow melt. Looks like it warms up a little bit. If you look, there's some little kind of rockfall things coming down off around the edges of that circle. And then finally, the 26th of October, we actually get a small rockfall event off of the headscarp. So again, the landslide didn't fail immediately after that, but if you were to see an increased frequency of events of this size, maybe across the landslide itself, that would be something we want to be concerned with. So we do keep track of these larger rockfall events. We have somebody log into the computer at least once a week, more frequently when other things start happening, and keep track of this. So we're building up a library over time of the frequency and magnitude of rockfall events on the Barrier Arm landslide. Okay, so we've worked our way through deformation, rockfall, and shallow landslides. Now this is where the wheels fall off for me, because I'm going to start talking a little bit about seismology, and I am objectively not a seismologist. But with the way we do that is we can measure the frequency, magnitude, and timing of rockfall and landslides and unusual noises and seismic activity using geophysics. So here we go. This will be fun. Okay, we've got this massive rock perched up on our steep slope on that cartoon on the left-hand side. It's ready to fail. And so as that landslide weakens, as we get into that curve of the progressive failure model, there's going to be rock damage that occurs. That rock damage produces short duration bursts of high frequency seismic noise. You don't hear that from afar, but if you have a seismometer sitting nearby, you theoretically should be able to pick that up and be able to discern it from all the other noise that's happening in the fjord. That's the research question right now, is can we actually identify precursory rock damage from nearby seismometers? And it's an open question. That's the fun part of science. But we do know that once that mass fails, you get impact forces from the mass moving down that slope. So as rocks bash into bedrock, that shakes the ground and it causes these seismic waves to occur. As the mass moves down slope, it also makes noise, and that noise is representative of a displacement of atmosphere. And so that creates an infrasound signal, so a subaudible signal that travels very long distances. And then finally, as you have grains that collide as the mass moves down the slope, you get a combination. You get both infrasound generated from that and seismic waves generated from that. And it's not really a simple seismic signature of these events. You get a lot of high frequency noise, so that graph that's up there on the left-hand side on the bottom of your screen, and then also that's superimposed on a lower frequency signal. So it's that waveform, or the frequency content of the wave as it's recorded at the seismometer, that allows us to make some estimates of the size of the landslide, where it originated, the direction it was traveling, those types of things that are really kind of cutting edge science. And some of this is 10, 20, 30 years old, but it's still a rapidly evolving subdiscipline. And so we use our infrasound array in the sound, as well as a couple seismometers, to get a sense of the infrasound and seismic signals that are associated with potential precursors to Barrier Arm. But it's a really noisy place. There are a lot of other things that can make noise that you see in the seismic data or in the infrasound data. So I'll start off with regional earthquakes. Those happen. We also get seismic data recorded from earthquakes across the globe. So it's a really noisy place, and Alaska has a heck of a lot of earthquakes. So we're kind of constantly filtering out what's a regional earthquake or a global seismism from our data set. We have two different glaciers that are always calving. There's ice falls, there's crevassing, there's popping and cracking. Those things make a lot of noise, the Berry Glacier and the Cascade Glacier. But then there's landslide-related things that make noise. There's the basal slip of the landslide itself, which you see on the failure plane at the bottom of the mass. You get rock fracture, rock damage that's occurring, so it's high-frequency, short-duration events. We've got rock falls, we've got debris flows, all of these things. So it's a really, really noisy place. So it's not easy to fully interpret the signal and say, this was a rock fall, and those rock falls are increasing in frequency. But we're trying. And so a colleague of ours up at the Alaska Earthquake Center, she recently completed her master's thesis, and the article hopefully will be coming out soon, where she looked at the velocity of the landslide as measured by the radar and looked for evidence that those short duration bursts of high frequency seismic noise were increasing as the landslide mass increased. And if so, then potentially we could use geophysics to say the landslide is moving versus the landslide not moving. And it's just another line of evidence that something's happening should that radar system go offline. And so she worked through the two different fall periods where the landslide was moving a lot and one where it wasn't moving so much, and was able to ascertain a clear difference between those time periods. This is research. This is not ready for operational use, but it is a promising tool that we might be able to put in our tool chest. And then finally, this one's a little bit more confusing because we have a couple of different things going on here. So we use infrasound to try to understand from the waveform of the data as they arrive at each one of the sensors what that source was. The rockfall has sort of a different pattern, different characteristic than snow avalanche does or a glacial calving event does. It sounds different, and in the subsonic, it also sounds different. So we're able to apply some machine learning algorithms to attempt to differentiate the sources of those signals based upon their waveforms and their frequency contents. And then, since it's set up in array, we can use how quickly the wave travels to each one of the sensors to pinpoint the location that was the source of that. So you probably can't see it, but that quarter of a polar plot there has things broken into the kite, the prow, the core, and the tail. And so as waves arrive at each one of those sensors, we can say, oh, it came from that direction. And then we know what is in that direction on the landslide. And so we can tally up the number of events that we have within a week and say, hey, this is increasing in frequency from last week, or it's decreasing in frequency from last week. And it's just another sign of what may or may not be happening when it comes to potential precursors. And then finally, one of the big things we want to do is we want to be able to detect an event should it happen. We want to know that a landslide occurred. And so another colleague at the Alaska Earthquake Center, Ezgi Karazozan, has a paper that'll be coming out very soon that deals with landslide in Surprise Inlet, so one of the next coves to the south of Barry Arm. So there's a stray blue arrow up there for some reason, but if we look in that yellow circle, that was actually a recent landslide, maybe 2 million cubic meters of material, so much, much, much smaller than Barry Arm, from last September. It actually broke off a chunk of the Surprise Glacier and created a small wave, very small, but was still detectable in the NTWC tide sensors in Port Wells and Barry Arm. So this landslide, even despite it being small, was actually picked up in the regional seismic network. So as you look at arrival times of different types of waves, you can pinpoint the location of the source of those. And Ezgi has built an algorithm that does this in real time. So her real-time landslide detector picked the location of this and was very close in both the volume of the prediction and the exact location of that prediction. So a small landslide was detected using geophysics. This is way more complicated, and I'll just fumble my way through it. So I'll just say that the infrasound was a little less clear. You really have to know what you're looking at, but the fact that it was a very small landslide probably complicated that, and the resonance of the wave as it bounces back and forth through these steep-walled fjords, that makes a difference too. So still some more work to do on detection using infrasound, but the seismic data were quite promising. So leaving maybe a minute or two for questions, I'll buzz through these. You'll see that we're doing a lot of things, we're learning a lot, but this is still an inexact and rapidly progressing science. We're figuring things out on the fly in landslides, but we're leveraging experience from scientists in Canada, Norway, Switzerland, and doing our best to be able to tease out what these potential precursors might be. So given that little lead time from landslide failure, wave generation, and arrival in populated places, we really do need to focus our efforts and investigations into understanding potential precursors. And then finally, this isn't all we do. We do a lot of other applied science and research where we're attempting to look at the hydrology, the climate history, glacial recession in advance to understand how that affects the slopes in Prince William Sound, coastal Alaska, and other cold regions of the world. And so with that, I'll leave this up here and acknowledge some of our partners throughout this whole process. And then finally, if you want more updates on Berry Arm, there's a list that you can sign up for below, and I'll open it up to questions now. Thank you.
Do you predict that the formation will fail in its entirety, or will it kind of partially fail? Is that a possibility as well?
That's the multi-million-dollar question. Yeah. The worst case scenarios when we do the modeling assume full failure of it. The landslide moves in different pieces. So one piece will move at one time and one piece will move at another time, which suggests there is some dependence, there's some independence of the different parts of the landslide. So we're not sure.
Hey there. So we're the predictive models that you're comparing the Berry Arm landslide to, those were lakes, correct?
I'm sorry,
I can't remember the name of it, but it started with an L. Was that?
Latuya Bay. Latuya Bay was so Latuya Bay was back in 1958, landslide triggered by a big earthquake, generated a huge wave in a relatively small bay that's maybe several miles long by a few miles wide.
Okay, so my question is there any relative size difference between like the Berry Arm and there versus Latuya Bay, and does expanding the size of that bay change the predicted wave compared to Latuya Bay?
Yeah, very good question. So I don't have the numbers committed exactly to memory. I think the part of Berry Arm that is immediately adjacent to the landslide is of about the same scale of the small part of the bay that was directly below the Latuya Bay failure. Berry Arm itself, Port Wells, Harriman Fjord, much bigger than Latuya Bay, and so that dissipation of wave energy is going to occur differently in Prince William Sound that it did in Latuya Bay, but it is constrained enough that all the models do show significant life-threatening waves pretty much anywhere beyond the terminal moraine out in Port Wells. Yeah. Good question, though.
I have a couple of questions. How fast is Berry Glacier retreating, and is that going to have much effect on your landslide?
That's a great question. So let me see if I can get back to just bear with me as I zoom backwards here. So the landslide itself, the glacier itself, if you look closely, there's an island on the leftmost side of the image. The glacier was on that island back in 2006. And it's retreated to its present position, which is about 3.5 kilometers from that island. The glacier terminus has been pretty stable since 2017. So 3.5 kilometers in 11 or so years, but it's been pretty stable since.
Okay, what about the part of the slide that's called the kite? If that were to fail catastrophically without the rest of it, would it lessen the load on the rest of the slide area?
Yeah, another multi-billion-dollar question. It seems as if the kite is somehow, the kite will move first in the periods that we've seen the landslide move. The kite moves first, followed by the prow and the core. And so it does seem as if there's some linkage between those different elements. So the question is, if the kite fails, does that mean everything else is stable, or potentially does that mean things are less stable? Is there going to be damage to the slope itself that may cause greater instability because of impacts from the forces above? So we call that impulsive loading. So if something falls onto something that was a little bit more stable, that could destabilize that part of the slope. And so that's something we're concerned about. And again, that's an open question as to the stability of the landslide should the kite fail.
Okay, one other question. There should be a submarine moraine out near the, I don't know, Point Doran or beyond.
Yep.
And that should attenuate the wave into Port Wells, wouldn't it? Quite a bit.
there is a dissipation of energy each time the wave passes over a moraine. It does have an impact. The models maybe don't treat that exactly right because they treat it as a solid mass when in fact it's moraine material. So there is going to be some potential for erosion of that during the event. So there is some dissipation of energy, significant dissipation as you go through multiple sequences of moraines and over bedrock ridges. So they do have an impact on the wave height itself. But with that being said, you're still seeing a wave multiple meters high out in Port Wells that is life-threatening conditions, dangerous currents, those types of things.
Dennis, we've got time for one more question, and we're going to take it from online. And it's, is there a warning procedure in place for potential recreators in Prince William Sound that may be in danger?
I'm so glad my
from a
friend and
landslide?
colleague Dave Snyder is here from the National Tsunami Warning Center, where he'll be talking a little bit about that, I'm sure.
So, thank you.
Thank you.